Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to demonstrate how to use Newton's laws and couple that with how to study motion. So in this example, right, we've got this person on this bike. In this example, we're going to assume they start from rest. They're going to accelerate down this 20-meter incline. Now I do want to point out that in my example here, I'm not intending this to be them pedaling really hard. We're going to imagine that they just roll, and we're going to talk about just gravitational acceleration. They roll down the incline here to the bottom, and we're going to try to calculate how long it'll take and what their final velocity will be at the bottom of the incline. All right. So for starters, in our picture here, as the person rolls down the incline, they're going to be moving faster and faster and faster. So one way that we may show on the diagram that that's happening again would be with a motion diagram. So I usually use just dots to represent the person. So as time goes on, this person's going to be moving, and because they're going to speed up, they're going to move further and further and further with each passing time frame. Right? So what's going to happen is their velocity vector is going to get larger and larger and larger. Right? And that's because the person is accelerating in the direction of the velocity. Right? To find the acceleration, what we're going to do is we're going to use Newton's second law. So I'm going to go ahead and draw a free body of the person. I'm going to use my little straight edge tool because it's really nice for that. The first force I always put in my free bodies is the gravitational force. Now the gravitational force, as far as how it's calculated, it's mg and it's straight down. So in this picture here, the first force we're going to consider is that one. Right? That's their weight. Now, remember that forces come in two types. There are field forces and contact forces. Gravity is a field force. Now we're looking for direct physical contact. And notice that there's contacts here and here. Those are going to create forces that we typically call normal forces. In all technicality, there's two of them, one on each tire. What we generally do with forces like that, when we're looking at cars and things like that, we generally lump the forces together and call them one normal force. Sometimes it's necessary that we separate them off into separate forces. Sometimes it's not. In this particular problem, it's not. So I'm just going to group those together, call it one force. And that force is going to be normal to the surface. So let's see, that's going to be something like this. Oops, draw that in black. So there's my force vector for the normal. And again, that's the sum of the two normals, one at this tire, one at this tire. Now, it's reasonably easy to show that this is 15-degree angle. I think that makes that 75, but remember these add to 90. That's going to make that interior angle right there 15 degrees. I'm looking at the person, and again, if we define our system as this biker, right, we've got the gravitational force as a field force. After that, we're looking for direct physical contacts. There are no other contact points. There's nothing coming across that green boundary, at least if we ignore air drag for this problem. And this is going to be a relatively low-speed problem, so I think we can throw air drag out without too much worry. So that's pretty well it. There is my free body, just two forces. Now, force vectors, when we add these things, we have to decide on a direction. And my standard rule of thumb for this, I call these carrots, Captain Rod's rules of thumb. My standard rule of thumb for writing Newton's second law equations is this: identify the acceleration direction, call that positive. This bike, if I were to draw its acceleration vector, it's accelerating that way. Therefore, that is the direction that I'm going to want to call positive. So I'm going to go ahead and put a coordinate system in this problem. X, Y. You can put that coordinate system anywhere you want. I just got to get it somewhere so that I can reference directions here. And now, the vectors we're looking at. We've got this normal vector. It makes a right angle to the surface. The normal vector is in the y direction. It does not have an x component. Right? But this gravitational force has both an x and y component. So what we need to do is we need to break that vector down into its x and y components. I'm going to go ahead and draw those in red. Right, I'll put these right kind of next to the normal there. All right. So if I were to take this vector and draw its x and y components, that might look something like this. And something like this, right? And they have directions as well. Right, so this guy right here, that's the x component of mg, so I'm going to call it mgx. This red one right here is the y component of mg, so I'm going to call that mgy. Whoops. Now I've kind of covered up my normal force there, but that's okay. We are not going to need it for this problem. Now, when we apply our Newton's second law equation now, sum of all forces x direction equals ma. And again, what I'm calling here, I'm looking at my coordinate system. Down and to the right is the positive x direction. When we look at our free body now, again, remember the normal force does not have an x component, but the gravitational force does. That's the x component of the gravitational force. Now, the trick here is focusing on this triangle right here. It's a right triangle. The hypotenuse is equal to mg. This side is opposite the angle 15 degrees. So that thing is going to equal mg, that's the hypotenuse, sine 15 degrees. Now when we write our Newton's second law equation, this is the only force in the x direction. So summing all forces in the x direction, we're going to have mg sine of 15, and that's it, equals ma. You'll notice that the masses divide out, so our acceleration is equal to g times the sine of 15 degrees. And if we go ahead and calculate that, I got 2.54 meter per second squared, using a value of about 9.81 meter per second squared. So there's our acceleration. Now, we've got all sorts of simplifying assumptions, like we have assumed no friction and air drag. So this 2.54, I'm going to go ahead and carry the 4, but that value right there is not really probably an accurate value. Our acceleration is probably somewhere in the 2.5 meter per second squared range. Ooh, pardon me. I'll go ahead and carry the 4 along, but again, we've got lots of assumptions that we've built in already that are going to make our results not completely true. But that's okay. I mean, the point of this is how do we do the analysis? And the same type of analysis can be used for more and more and more complex examples. But for this one here, we're just going to assume air drag is small and friction is small and focus on fundamentals. All right. Now the million-dollar question here, what do we do with that acceleration? So the next part of this problem is studying the motion of the biker. And to do that, what I'm going to do here is I'm actually going to redraw my coordinate system. I'll explain why here in a moment. Oops. All right. What I'm going to do now is draw a new coordinate system for the purposes of studying the motion of the bike. I'm going to go ahead and do that in green. And this is now what I'm going to call my x direction. We're not going to need the y coordinate, but I'm going to go ahead and draw it anyway. Our y coordinate would be looking something like this. Right. So now I'm going to use the green set of coordinates to track the motion of the bike. Now the reason I moved it, the previous coordinate system I had here, I was just using it for directions. This one I'm actually going to use to study the motion of that biker. And I moved it so that at t equals 0, the biker's starting from the coordinates of 0, 0. Right. So now, when we draw our velocity graph, let's see, I guess I'll do that right here. Our velocity graph is going to look something like this. Alright, so we're going to draw, again, we're graphing velocity against time, taking note that at t equals 0, the velocity is 0. Also noting that our acceleration is constant. Now, when our acceleration is constant, that's going to give us a linear velocity curve. So this is going to look something like this, out to some time t here. Now, we know that the acceleration is 2.54 meters per second, and what that gives us is it gives us the slope of that line. Remember, acceleration is the slope of your velocity, and the intercept is 0. Therefore, the equation of that line is v equals 2.54 t. I'm going to put a little NCU here for note consistent units. All right. Our position graph then is going to look something like this. Give me a moment here. So again, what I'm going to do now is sketch a graph of position against time. In this case, the position is measured by our x coordinate. And this graph is going to have some concavity because the person's moving faster and faster and faster. So every delta t that goes by, the distance that they're covering is getting larger and larger and larger. So this graph is looking something like this. It starts at 0, 0. That's a consequence of me putting my origin here. Right? Now, as far as this equation here, how do we get that? Well, the relationship between velocity and position is this. The delta x is going to be given by this area right here. And that area is equal to 1/2, right, base, which is t, times our height, which is 2.54 t. So our delta x, which we can write as x final minus x initial, is going to equal 2.54 over 2 t squared. Okay. Next step in this problem, I'm going to go ahead and just write it without the 0 here. So now we have x equals 2.54 over 2t squared. Next part is just put in our value for x. X is 20 meters. And I'm going to remind everybody units are consistent, so I can go ahead and put in 20 equals 2.54 over 2t squared and solve that for t. When we solve that equation for t, what I get is about 4 seconds. I'll put approximately 4 seconds. We can now take that time and go back to our velocity function. Insert that right there, and we're going to get a v final of approximately, when I run this, I get about 10 meters per second. So at t equals 4 seconds, our biker is here. The velocity vector is now this way at about 10 meters per second. So, important points of this problem. Notice there's 2 distinctly different sets of physics taking place. We had the free body and Newton's second law. And getting back to that, those are the black force vectors here, the mg down, the normal, which is kind of covered up here by that component, but that normal is kind of up and right. Again, normal makes a right angle to the surface. Normal is just kind of a fancy word for right angle. In this case, we broke the gravitational force down into x and y components, and we did that because of the acceleration direction. The acceleration direction is pointing right down the incline. Therefore, we aligned our x-axis with the acceleration. That's one of my standard rules of thumb. Always align one of your axes with the acceleration direction. This force vector can be broken into these 2 components, right? mgx, mgy. The mgx is opposite the 15-degree angle, therefore it's equal to mg sine 15. The mgy we didn't need. In this particular problem, the mgy is adjacent to the 15, so its magnitude would be mg cosine 15 degrees, but we don't need it for this problem. This ends up equaling our net force, which allows us to find the acceleration. So there's the first part, the first set of physics, the Newton's second law part. Then the next set is the motion study. What do we do with this once we find the acceleration? What is that good for? Well, we can use it to draw a velocity graph, and then we can use our velocity graph to draw a graph of position versus time. And then we typically use concepts of area. Remember, the area bound under your velocity curve here is going to give you the change in position, and that's what we use to find our function here, like x against time. So I hope this video helped demonstrate these concepts. Everybody have a great day.